This is Steve Fitzgerald, and I will be your instructor for the fire science module. This is an important topic as it provides the background for many of the other modules that you will go through in the Citizen Fire Academy training. The module will also be useful for you as you develop your wildfire preparedness action plan, which is a part of this Citizen Fire Academy training. So we're going to be covering a lot of topics here. The first is hazard versus risk, sources of fire ignition, historic fire regimes, the anatomy of a fire, fire behavior 101, various kinds of fuel characteristics, weather, topography, and how fires progress, as well as fire intensity versus fire severity. You're going to hear a lot of new terms during your training. And two terms that you often hear but are used interchangeably are risk versus hazard, and they are not the same. Hazard is the potential source of harm, and hazard can come in many forms, but for us, wildfire is the hazard that we are primarily concerned about. Risk, on the other hand, is the probability that exposure to a hazard will lead to a negative consequence. Risk is a function both of hazard and dose, or what we call exposure. So, for example, you could have a high hazard, say with high fuel loads in Northwest Oregon, that could potentially fuel a wildfire, but actually have a low risk because the fuels remain unburnable for a good part of the fire season, and lightning ignitions are rare in that area. Historically, wildfires came from Indian burning and lightning. Indians set purposeful fires to modify their environment to enhance food and medicinal plants, stimulate browse for horses and game, and also for hunting, and used for warfare and communication. Lightning is a very important ignition source today. Some 45,000 thunderstorms occur around the globe each day with the potential to ignite a wildfire. Lightning is still a major ignition source that fire agencies have to deal with. However, a significant number of wildfires, both big and small, are ignited by humans. Humans doing things with fire that they shouldn't be doing. Here in Oregon, storms track from the southwest to the northeast, and this is known as Lightning Alley. Within this zone, the probability of lightning strike and potential fire starts are high. Add high fuel loads and homes intermixed within that, and this area or region is at high risk to wildfire. Here's a table compiled by Keep Oregon Green to give you an idea about the types of fires, the numbers of fires, and the acreage and the costs of suppressing human-caused wildfires in Oregon. Although a variety of natural disturbances have shaped our forests over time, wildfire has had one of the most profound effects. We know that historically not all fires were the same. Some burned much hotter than others, and some forests burned more frequently, but the fires were less intense. Forests that historically burned frequently but with low intensity include the Willamette Valley oak, and the drier conifer forests like ponderosa pine. High severity fires occurred in the state's wetter regions and higher elevations. These fires were very intense, killing most of the trees. Historically, they occurred infrequently, only every 100 to 450 years, but were often very large. Some forests had a history of both low and high fire severity, and these forests typically burned every 40 to 80 years. Sometimes the fires were confined to the surface, other times they climbed into the crowns, killing all the trees. When wind is present, fires will move or be pushed away from the point of origin in more or less a straight line, if you notice the green arrows on this diagram. And this is called a heading fire. Heading fires can spread very fast, and it's a dangerous place for firefighters to be. Flanking fires form the sides of these fires. From the point of origin, the fire will also burn into the wind, or what we call a backing fire at a slow rate. And you can see the backing fire at the bottom of the diagram. So let's talk a little bit about fire behavior. So a couple of things. One is that to sustain a fire, you have to have three things. You have to have a heat source or ignition source, oxygen, and of course fuel. When all these three are present, then you can support a fire. If you take one of these away, the fire will go out. So for example, to take oxygen away, we might use a chemical fire extinguisher, and that would remove oxygen and the fire would be extinguished. Another important triangle is called the fire behavior triangle, and it's comprised of topography, weather, and fuel. When I talk about fire behavior, I'm talking about how fast a fire moves, that is the rate of spread, the flame length, which is a surrogate for intensity, whether the fire is torching, crowning, spotting, or whirling. But if we have an ignition, how that fire behaves is really affected again by these three factors: topography, weather, and fuel. So if the weather gets hot and dry, or it becomes windy, is that you'll see a corresponding increase in the rate of spread of the fire and its intensity. Likewise, if the fire gets cooler or wetter, is that the fire intensity and how fast it moves will be diminished. And oftentimes we can use these cases where firefighters can then help find places to corral the fire when the weather conditions are favorable. But the one thing that is in common between these two triangles is fuel. It is the common denominator. And it's really the only thing that we can really manipulate to prevent or reduce the intensity of fires, both in and around neighborhoods and across the landscape. So there are three modes of heat transfer, that is, transfer of heat from the ignition source to fuel. And this includes convection, conduction, and radiation. And I think most of you have experienced all three of these from a campfire. When we look at fuel, we can break them down into fuel types, but for forest and rangeland fuels, they can be categorized from ground fuels up to tree canopy fuels and everything in between. Another fuel type are natural fuels versus what we call activity fuels. And activity fuels are comprised of slash that have been created by forest management operations. Important fuel characteristics that affect fire behavior include, of course, the moisture content of the fuel, the particle size and diameter, and the surface area to volume ratio of various kinds of fuel, the amount of fuel per acre, or what we call fuel loading, and the fuel arrangement and its continuity, that is, vertical and the horizontal distribution of fuel, and also the chemical makeup of the fuel. are there volatile oil, sap, and pitch within the fuel that might enhance its combustibility. Also remember that homes are fuel too, and they possess many of the same characteristics of fuel that we just went over in the previous slides. We will go over this more about the combustion of homes in the Home Protection Strategy module. Slope affects how fuels are heated. On steep slopes, the fuels are tilted toward the flaming front, making much easier for the preheating and drying of fuels ahead of the fire. Thus, fires can move much more quickly upslope than down, unless there is a wind pushing the fire down slope. The aspect, or the direction the slope faces, and the elevation affects how fuels are exposed to sunlight or heat, which affects their wetting and drying. Vegetation and fuels on south slopes dry out much quicker during the summer season than those on north slopes. Fuels in lower elevations tend to dry out sooner than higher elevations due to differences in temperature. When a fire ignites on a slope, it can affect its behavior. A fire that ignites at the bottom of the slope can gain a lot of momentum going uphill, such that the fire can be very intense by the time it reaches the upper slope position. But other kinds of landscape features that it can affect fire intensity and its movement include whether you're in a canyon that creates a chimney effect, and here are some examples. Whether you're at a saddle where a fire then is moving upslope and over and through that saddle. And of course other features such as narrow canyons where radiant heat can ignite fuels on the other side of the canyon and exacerbate the condition. But there are also other landscape features that can be used to help corral or stop a fire. Various kinds of barriers, which include rock slides, rivers, roads, and maybe changes in vegetation, like on the clear cut where there's very little vegetation at this point in development versus the more mature forest that you see adjacent to the clear cut. All of these can be used in trying to set up fire lines to help control a wildfire on the landscape. Wind can increase the oxygen supply to fire and dry fuels quicker and influence the direction and speed of the fire. Certain types of wind events are particularly dangerous, such as east winds in Oregon and the Santa Ana winds down in southern California. Of course, precipitation is very important, both the amount and duration, which affects the wetting up of fuels. The amount and duration of precipitation affects the length of time that fuels take to dry when precipitation stops. In years of low precipitation, fuels dry out much sooner in the summer, making for an early fire season. Of course, temperature also profoundly influences drying too, once precipitation has stopped. A strong marine layer near coastal areas can also affect the wetting and drying of fuel both on a daily basis and throughout the summer. On a daily basis, Relative humidity affects the wetting and drying of fuels, and therefore their ability to combust. Fuels tend to be moist in the morning when relative humidity is at its highest. However, by afternoon, the relative humidity drops and fuels become drier. This is why you see much more active fire behavior, such as a large smoke column, in the afternoons on warm days. The speed at which fuels dry up or wet or become wetter or more moist with respect to relative humidity depends on the fuel particle size. So, for example, you can compare needles and grasses versus large sticks. Needles and grasses, their moisture content will change much quicker because they're smaller than, say, larger sticks or small logs. Fires can progress from the surface into crowns. In any given wildfire, the fire may start as a surface fire and transition into a crown fire and then back again. This process can be repeated many times during the life of a wildfire and is dependent on weather, fuel, and terrain factors. So here's what you might expect during the course of a wildfire. A surface fire here, they are very, very common in a wildfire. Crown fires, sometimes called passive crown fires, and this would include torching that you see here, is also very common. Active crown fires, where fire is now moving through the crowns and is supported by heat and fire on the surface, are also very common. And sometimes you can get crown fires that are independent of the fuel and fire beneath and begins running actually through the crowns, where one crown combusts the next crown, and usually this is under on a slope or under very windy conditions. These independent crown fires are usually uncommon, but they're short-lived. But when they occur, they're very destructive. We will discuss next what factors affect how a surface fire can transition up into a crown fire. Three factors determine whether a surface fire will climb up into the tree canopy. The first is foliage moisture. The earlier in the summer that it turns hot and dry, the quicker the foliage becomes drier and more fire prone. The second is surface flame length. The more fuel there is on the surface, the greater the flame length, and the more likely a fire will reach the tree crowns. The third is the distance from the ground to the bottom of the tree canopy. The higher the canopy, the greater the flame length needed to reach the crowns. Three factors, a few factors also affect how, once a fire gets up into the crown, whether it'll actually spread through that crown from tree crown to tree crown. And that includes its rate of spread, which is influenced by weather and topography, as I previously mentioned. So with wind or a steep slope is that you can get fire moving up and combust one crown, and that's enough heat to then combust the next crown, and so it's like a domino effect through the canopy. But the other aspect of this also is crown density. If a stand is thinned or you break up the crowns by thinning, is that you can reduce the ability of a crown fire to propagate itself through the canopy of the forest. When fuels are continuous, both vertically and horizontally, a wildfire can burn through the fuel unchecked. This slide illustrates a continuous vertical arrangement of fuel called a fuel ladder. A fire that ignites on the ground can quickly climb up into the small, medium, and eventually large trees and then become a crown fire. There are several treatments to moderate both surface and crown fire potential and their severity, and these include pruning, mechanical treatments, thinning, pile and burn or pile and chipping, and prescribed fire. If you can change the arrangement and continuity of fuel with those treatments, you can also change the behavior of the fire. Here, a wildfire moved as a crown fire from the left to the right. In the middle, it encountered a stand that had been thinned, pruned, and the slash removed. When the fire spread into this area, it dropped to the ground and underburned the treated area. However, when it encountered heavy and continuous fuels on the right side of the treated area, it became a crown fire again. Although this treatment did not stop the fire, it shows that manipulation of fuel can affect fire behavior. To really affect a fire's behavior, more area would need to be treated, which is the thrust of city, county, state, tribal, and federal agencies. Let's talk briefly about fire intensity and fire severity, because they are different. Fire intensity refers to the amount of heat released in the flaming front over a given time period. Often it is referred to as high, moderate, or low fire intensity. Flame length, shown here in the diagram, can be related to fire line intensity, which can be quantified, but it is difficult to measure and usually done in experiments. Fire severity refers to the effect of fire intensity on soil and vegetation. Again, it is often referred to as high, moderate, or low fire severity. We typically use visual indicators of severity, such as the amount of bowl or crown scorch. The higher the crown or bowl scorch, the more intense the fire and the greater the negative effect on the tree or plant in question. For soil, we look at the amount of soil exposed, the color of the soil, which indicates a loss of organic matter. We can assess water repellency, as shown here by scraping the ash off to expose the mineral soil below and putting a little water on the soil surface. If it beads up and stays beaded up without infiltrating into the soil, we can conclude that the soil has developed a hydrophobic condition, meaning soil is less able to absorb the water. Now, this can be a problem in the following weeks or months if there are high rainfall events where the water won't infiltrate in the soil and instead begins to move across the soil surface and begins to erode and move sediment and can become a debris flow, which then moves into streams and ravines and streams. To summarize this module, it all comes down to understanding the fire and fire behavior triangles. Fuel is the common denominator for both triangles and is one of the factors that we can manipulate. Manipulating fuel around your home can affect both fire intensity and fire severity. What I've presented here about fire science in this module is really about the physics of fire and the physics of fire combustion. For more detailed information on fire behavior and fuel, you can find it here in this publication, which you can download at your convenience. Thank you for listening.